Let us now discuss principal strains. Principal strain is an important concept that describes the maximum and minimum elongation or deformation in a material along specific directions. In three-dimensional space, principal strains are the strains that occur along the principal directions where the strain values are either maximized or minimized. We have already discussed that the strain acting at this reference point P changes with the inclination of the plane passing through this point. When strain variations are determined analytically, a plane is passed that cuts the original element into two parts and condition of compatibility is applied to the to either part. Thus, if we consider a cube element extracted from the body and pass a plane ABC at reference point P in such a way that the original cube element is divided into two parts, we can then apply the conditions of compatibility at point P and correlate the deformations appearing at plane ABC with the deformations appearing at the faces OAB, OBC, and OAC. In mechanics, we have the so-called compatibility conditions, which guarantee that when a body deforms, the strains are compatible in such a way that no discontinuities or gaps are generated inside the body as it deforms. We can also understand the concept of principal strains using the analogy with sphere and ellipsoid. If we imagine that a body before deformation has got a point of interest where infinite number of vectors are radiating out in such a way that all these vectors are of same magnitude. These vectors show the direction of infinite fibers that are connected to the origin. Since no load is applied on the body, therefore all these deformation vectors are of same magnitude. Now, if load is applied, these vectors would then change their direction and the magnitude of these vectors would also change. Thus, instead of these vectors being arranged in a sphere, they will form an ellipsoid because some of the vectors would get squished, some of the vectors would get stretched, and some of the vectors would change their directions. However, there are some vectors whose direction don't change after the application of the load. They are only stretched or squished. Thus, if we imagine vectors n1, n2, and n3 in this small body of sphere, after application of the load, these three vectors stay in the same directions. However, vector n1 get squished, vector n2 gets stretched, and vector n3 also gets stretched. These directions are called principal directions. These are the directions at which there is no shear strain. We can also understand this concept by using 2D analogy. Imagine we have got a circle within a body that is getting stretched. The two vectors which are shown in green have got same magnitude before application of any load. After the application of the load, we can see that the two vectors change their magnitude, but its direction stay the same. Also, the angle between these two vectors stay the same after the stretch. More specifically, before the stretch, the angle was 90 degree. In other words, these two vectors were orthogonal to each other, and after the stretch, the angles stay 90 degree. That clearly tells us that there is no strain deformation in these two principal directions. Therefore, we can say that in the principal directions, we have got no shear strain. The idea of the principal strains can be demonstrated by using eigenvalue problem. Thus, using our sphere and ellipsoid analogy, we can say that when a strain vector is multiplied by a certain vector whose direction cosines are given as lmn, then after deformation, there is only change in the magnitude of the vector lmn. The direction of lmn stay the same. Please note that all the other vectors beside n1, n2, and 3 have got their magnitude and direction both changing. In other words, in all the other directions, we have got shear strains. In mathematics, this problem is called eigenvalue problem. So in the eigenvalue problem, we have got the strain vector applied on a particular vector whose direction cosines are L, M, and N. This must be equal to a scalar times the same vector. So this is equivalent to saying that we have a particular vector which is shown in green that is multiplied with the strain vector, and as a result we have only the change in magnitude of that vector. The direction of that vector stay the same. The eigenvalue problem implies the following three equations. Thus, the strain rho is multiplied with this vector and we get L strain 1 1 plus M strain 2 1 plus N strain 3 1 is equal to L times the scalar. Similarly, L times strain 1 2 plus M times strain 2 2 plus N times strain 3 2 is equal to M times the scalar. The last equation is L times strain 1 3 plus M times strain 2 3 plus N times strain 3 3 is equal to N times the scalar. The right hand side value can be brought to the left hand side and L, M and N be taken as common as shown in the following three equations. After this, we can take determinant of both sides, and solving this determinant, we will get the so-called characteristic equation in terms of I1, I2, and I3, which are defined as follows. The epsilon shown in the characteristic equation is the same scalar which was getting multiplied in our eigenvalue problem. This scalar is called eigenvalue, and the vectors which are in the principal direction, they are called eigenvectors. The coefficients I1, I2 and I3 are shown below. I1 is summation of the diagonal terms of the strain tensor. I2 is the sum of the cofactors of the diagonal terms. I2 can be worked out as strain 1 2 square plus strain 1 3 square plus strain 2 3 square minus strain 1 1 strain 2 2 minus strain 1 1 strain 3 3 minus strain 2 2 strain 3 3. I3 is the determinant of the strain tensor. From the property of roots of cubic equation, we can work out our I1 equal to the scalar epsilon 1 plus scalar epsilon 2 plus scalar epsilon 3. I2 would be equal to scalar epsilon 1, scalar epsilon 2, plus scalar epsilon 2, scalar epsilon 3, plus scalar epsilon 3, scalar epsilon 1. I3 is equal to scalar epsilon 1, scalar epsilon 2, and scalar epsilon 3. Please note, scalar epsilon 1, scalar epsilon 2, and scalar epsilon 3 are the eigenvalue. These are the scalar values which we will get from our characteristic equations. I1, I2, and I3 are the invariants of the strain tensor. That is, their value would be the same regardless of rotation of the coordinate axes. It is also important to note that the three equations given here are not independent. In the case of structure mechanics, only 2 out of 3 of these equations are independent. That is the reason we get the determinant of all these three equations equal to 0. Please note, having determinants of any equation equal to 0 mean that the equations are not independent. There is minimum of one equation that is dependent on the other two equations. Thus, after solving the characteristic equation and working out the eigenvalues, we can plug the eigenvalues back in these equations. However, we won't be able to get the required eigenvector for a particular eigenvalue. Therefore, we need an additional equation which is independent of the available two equations which are also independent. The additional equation can be got from the identity L square plus M square plus N square equal to 1, where L, M, and N are the direction cosines. Thus, to summarize, after getting three values of the eigenvalues, we can plug the eigenvalue back in these equations. And using the identity L square M square plus N square equal to 1, we get three independent equations and three unknowns, that is L, M, and N. Once they are solved, we get the eigenvector for the particular value of the scalar eigenvalue. We have to repeat this exercise for 2 more times in order to get the three eigenvectors which will be in the corresponding three principal directions.